Hi everyone, we're here today with Simon for another software engineer mock interview. Thanks so much for being here with us today, Simon. Can you quickly introduce yourself for our viewers?
Yeah. Hi, folks. I'm Simon Eisman, and I'm a principal software engineer at a fintech startup called Monarch Money. In the past, I've worked across the stack at Google, Spotify, and Bloomberg, and looking forward to the interview.
Yeah, I think we're really looking forward to the wealth of knowledge that you have to share with us. All right, so let's get started with our question. Our question today is find the number of rotations in a circularly sorted array.
So when we say circularly sorted, I assume we mean that we have a sorted array to begin with, and everything is sort of moved over in some way.
Yeah, exactly. We have an example here for you, actually. So if you look at the example at the top of this whiteboard, you can see that if you start from the six that's in the fourth position, and you go right and around the array, it's actually sorted starting from the six. So because it's been shifted three to the right, the correct answer is three.
Got it. And we're specifically considering just the rotations to the right. So it wouldn't ever be backwards or anything like that. So if, for
Yep.
example, I don't know, if we had something uh, something like this, this would be 7, not 1.
Yes, correct.
Are duplicates possible?
For now, let's just say that they're not.
Okay, sure. I'll ignore it for the time being. So I suppose one approach that would solve the problem right off the bat that comes to mind would be something like a linear search for basically the inflection point in the array. Basically that point at which it goes from being the largest number to the smallest number.
Gotcha. So that sounds like roughly correct to me, but do you have an idea of what the runtime complexity on that would be?
Yeah, the runtime would be O of n time complexity in the worst case. I have a feeling that we could probably do better there.
Yeah, that makes sense. But we can start out by implementing that solution first, and then we can improve it later on.
Okay, great. Yeah, let's jump into it. So we want to do a linear search. So we're given this array. So let's define rotations. We're given an array. And I'll assume that the array that's provided to us is circularly sorted. So let's do an iteration. Let's do for this. And then what we're basically looking for is that inflection point where it goes from largest to smallest. So it'd be something like if the array at index I is bigger than the array at the next index, then I think we're done. We found what we're looking for. So if we're looking for, in this example here, we're comparing, let's say, the 100 to the 6. We want to return the 6 index, which is indicated here. So we would do return I plus 1. And I'm assuming if we don't find any rotations or we have maybe some edge cases, then we simply return 0, let's say. So it's already sorted or something like that.
Sure,
So
that makes sense.
all right, great. So now would be a good point to test this. So I'll probably come up with a couple of cases. Let's take a look. So I'll just define kind of like a test suite. So test find rotations. So let's kind of think what cases we want overall. We want a bunch of general cases where we kind of have it all sorted how we want, where it's kind of at various points in the array. And then we also probably want some edge cases. So things like what happens when it's empty, what happens when it's just one element, what happens when it's already sorted or something like that. So let's kind of write those out. So let's do an assertion. So find rotations. And let's do a simplified example. So like, I don't know, 6, 1, 2, 3, 4, 5. That's simple enough. And in this case, we want something like this being 1 rotation. So we'll say test failed. And the reason it's failed is the kind of situation we have here. So like a low rotation count. Yeah, whatever, low rotation. We could do a couple of other cases like this. So let's say it's a little bit further into the array. So we have something like 3, 4, 5, 6. And this would be 1, 2, 3, 4. So the answer here would be 4. It's too high. And let's just test these. I mean, there's probably a bunch of cases we'd like to test, but let's test these for now.
Mm-hmm.
So what we want to see here is not any assertion errors. So let's just do an overall print here. So something like all test cases passed. Okay, excellent. So let's put in a couple more examples. I think one set of issues that comes to mind that we definitely want to test for in the general case is that this is an even amount of elements in this array. So let's try an example where it's an odd number of elements. So let's say 7. So let's say in this case we have something like, I don't know, a similar situation. So 6, and then similarly here we have something like 7. Even. Just make this a little bigger. And then odd. Okay, swell. So that would be low count, even count, and let's say, just for argument's sake, let's say we want this to be completely rotated around. So something like this, where it's just at the very end. So I don't know, something like this, just a small case, just for argument's sake. And this would be 1, 2, 3, 4, right? Yeah, okay. And then similarly, let's do something like this, and that would be 5. All right, and the test cases that I talked about. So we want the empty case, we want a single element case, and we want a situation where it's completely sorted.
Right. Mm-hmm.
So we'll do that. This should just be 0. So empty case. Let's do 1, and let's do 1, 2, 3, 4, 5, right? All right, excellent. So fingers crossed. Let's hope this passes. High rotation odd. Okay, so it looks like this case failed. So I see. So it should be 1, 2, 3, 4, 5. So this should be 5.
Yeah. Mm-hmm.
All right, let's try that again. Okay, so we passed that case, but it looks like we're failing the single element case. Oh, well, that makes sense. Looking at the code here, it looks like we actually have an off by 1 error here. So we kind of should be looking just up until the pre-last element so that we can look at here. And then this would actually like fold back into this case and return 0. So let's try that again. All right, excellent. So it looks like it passes in these cases.
Okay, perfect. Yeah, we talked a little bit before about how this is a linear time solution, right? Do you think you can do better?
Yeah, definitely. I mean, we can definitely optimize the code from a linear solution. My hunch is that we need to do some form of a binary search here. Usually, when an
Okay.
array is sorted like this, binary search is a tool that we reach for.
Yeah, it's a good hunch. So, what would the binary search be looking for specifically?
Yeah, so in this case, what we're effectively looking for is, like I said, the inflection point. So what we're looking for is the minimum element in the list. Um,
Mhm.
Binary search sort of starts by, taking your whole data set and then diminishing the size of the problem at each step by sort of partitioning in some way between the start and an end. Um,
Mhm.
and I suppose that like one key insight here is that if the if the beginning of the array is like smaller than the end, like we have here in all these cases, we kind of know that it's already fully sorted. Like if the array, let's say in the sorted case, like here compared this one to comparing this five, we know that it's sort of sorted. But if it's not, it means that we need to kind of continue doing a binary search. So I guess that's because of like the sort invariant. It's not possible for there to be an element bigger than the last one in the middle, right?
Okay, yeah, I was just gonna ask like what the sort invariant is specifically.
Yeah, yeah. I think in this case, because the element, if the element is bigger in the front,
Mhm.
then it needs to be someplace in the middle. We can kind of do like a proof by contradiction, basically. If it were possible, then it would mean that
Mhm.
the minimum is somewhere in the right half, and the last element must be smaller than the first element. So like we kind of rely on that sort invariant.
Right. Okay, that makes sense. Yeah, it's very similar to what we use in like the first implementation, right, to decide where to look.
Right, exactly. And I think what's
Mhm.
helpful here is that we have this entire test suite here, so that even if we change the underlying
Mhm.
implementation, we'll kind of make sure that the test suite still works.
Yeah, absolutely. Okay, so I'd love to see you implement that then.
Yeah, for sure. Let me actually do a couple of examples first, just to kind of get a sense of what the condition that I need to use in our binary search is. So let's just
Great.
kind of
I think
do
that'd
a
be
couple.
helpful. Okay.
So let's say I have an example like what we had before. So like 6, 1, 2, 3, 4, 5, right? So here, let's say this is the start, this is the end. That means that the middle would be right here when we first start. Technically, the middle is between these two, but we always kind of go backwards. Um,
Okay, so these are like the pointers that you're keeping track of then?
yeah, exactly. So this would be the
Mhm.
start, this would be the end, and this would be the midpoint for our initial binary search. Um,
Okay.
as we kind of go down, we we can tell that in this case, the middle element is less than the start element. So in this case, we know that the inflection point is somewhere in our left half. So the binary search devolves to basically this. Um, and in this case, we can still see that the binary search is less than the start. Um, so we get something like the midpoint moving backwards. And then here we kind of get to our sort invariant where we see that something is bigger than this one, than, uh, than,
Mhm.
the, than the start. And then we know to stop. Uh, let's kind of run this against another example. So let's say it's not in the left half, but it's in the right half. So something like, I don't know, 3, 4, 5, 6, 1, 2. So something like this. So again, we start here. Then we have the end here. So we know in this case that um, the middle is larger than the start. So we should start looking in the right half. So um, our start ends up being either here or 1 over. So there's kind of a couple of ways you can do binary search. Usually I like to keep it the same way. So if I'm going into the left half, I kind of do the same index as the midpoint. And if I'm doing into the right, I just move it 1 over. It just kind of keeps it consistent implementations. So in this case, this would be the midpoint. Now in this case, we have the situation from before. So the midpoint is actually smaller than the start. So we go back, and then we see that our midpoint is still here, and our sort invariant is breached. So the answer would be 1 plus the midpoint. Okay. This is all well and dandy. So except in this case, we've only been doing even cases. So just to make sure I'm on the complete right path, let me do this with a with an odd number of elements.
Great.
So something like 2, 3, 4, 5, 6, 7, 1. Okay, great. So again, start. This would be the middle. This would be the end. In this case, we see that the midpoint is larger than the start. So our start ends up going over here to the 6. And then we get this. We see that it's larger. That means that the midpoint moves over all the way to the right. So then this way is the start. The midpoint maintains its position. And then we have the same case. So the invariant is breached, and therefore our answer is this index position right here. Okay, so perfect. I think, yeah, this makes sense. So we kind of keep comparing the midpoint to like the beginning, and then that tells us which direction to move.
Right.
Okay. All right, excellent. So let's implement this. I will rename this function so that we can use the same test suite without making anything different. So let's do find rotations linear search, and then we'll keep this name the same. All right, so you can do a binary search in a couple of different ways. You could do it iteratively, you could do it recursively. I think I'd like to do it iteratively right now, but I think a recursive solution would also work if we wanted to do that. So we have our start, we have our end. The last index should be, let's say, this. And let's think, we probably want to cover some edge cases, just some of these edge cases to start with, right? So if it's sorted, we know that, the start is always less than the end, right? That was the beginning invariant that we talked about, what always must be true. So then in this case, there is no rotation, so we just do return 0. And now we can actually do like the bulk of iterating in the loop.
Okay.
So I prefer to do this condition while the start is less than the end, because whenever they're equal or the end is smaller than the start, that's kind of when you stop. In this case, you would do something like return 0. But in the course of doing the loop, you can actually figure out where you need to stop your binary search. But I like to do this condition for my implementations.
Okay.
Let's do the calculation for the midpoint. That's just the start plus the end divided by 2. One small note about this is that actually this could lead to overflow issues potentially. There's essentially like another way of calculating the midpoint. I believe it's something like you start at the start and then you just add half of the difference. So it's start plus end minus start divided by 2. Yeah, so technically the reason that you get overflow issues here is that if your end and your start are sort of large enough, you might exceed the maximum. This can definitely be an issue with many languages. So it's actually safer to do something like this.
Yeah, that's a good point.
Yeah, so let's comment that out. And the reason we do this, of course, is to like truncate in case it's the even case.
Mm-hmm.
So
you're essentially like rounding down, right?
yeah, exactly. The truncation brings it down to, in our examples here, when you have this odd case, this even case, the midpoint here is technically in the middle, but you want to kind of go back down to the 5 instead of the 6 here.
Right, yeah.
Right. Okay. So now we can actually start doing the actual binary search where we diminish the problem size every time. So our case before was, if nums at the start is less than nums at the midpoint, right? That's kind of what we saw in these examples. Then what does that mean? It means that we have to go to the right half. So the right half basically means moving the start to mid plus 1. Otherwise, we look in the left half, which means we do end is just the middle. So that's kind of how we moved in this array. Now, it actually feels like something's missing here. I think we actually need to do that check. So we kind of hit this case a lot in our examples here, where when we found the midpoint to be greater than this, we know that we have to return the next element over from the midpoint. So we basically have to have a check that does something like if nums at the midpoint is greater than the nums at the midpoint plus 1. And then we can, that's basically our, kind of like our base case in a way. We simply return the midpoint plus 1. Oh, okay, so actually we need to move this above. I think, yes, we have to move this above, because otherwise these may not work. Okay, so I think this makes sense. So let's give ourselves some comments here. So this is the situation when the midpoint is, about the inflection point, right?
Mm-hmm.
Okay, great. So I think this would work. I'm ready to test these against our test cases if you are.
Yeah, let's give it a shot.
All right. Oh, yes, nums. Let's just rename this to nums. All right, one more time. Okay, so we have one situation that's failing, an index out of bounds. So that's for the empty case. I see. So at the empty case, okay. In the empty case, this would become -1, and then we're basically doing an incorrect comparison here. So we just have to special case it. So if the length of the number of elements we have is 0, then we can simply return 0. And I think that should solve it. Okay, excellent. So it looks like this would work. Give us the number of rotations.
Okay, amazing. You did a fantastic job. So I don't think I heard you mention, what is the space and runtime complexity of this final solution?
Right. So the runtime complexity of this in the worst case should be log n. I don't think that there are any cases that would bring us back to a linear point, because we're not allowed, or one assumption we made is that we can't have duplicates inside of this array. I think in that case it could potentially devolve down to linear time, but in our situation we actually may need a slightly different implementation here altogether. But this should be log of n for our binary search. And from a space complexity point of view, we're not using any extra space here. So it would be constant. If we had something like a recursive implementation, then it may have devolved down into like the number of stack frames, how many recursive calls we're making.
Right.
But in this case, it would just be constant because we're doing an iterative solution.
Right, perfect. And I'm curious, we also talked very briefly in the beginning about whether or not there might be duplicates. Would your solution change at all if there were duplicates in the input?
Yeah, definitely. So that's a more complicated case for sure, because if you have duplicates, I think some of these invariants that we're using won't fully make sense. Like for example, I can think of a scenario like two, 1, 1, 1, 1, 1, 1, something like this.
Mm-hmm.
This wouldn't always tell you exactly where you need to go. I think so our implementation would definitely change, because in the worst case, you may have to do something like a linear search, because you can't always tell where the inflection is.
Mm-hmm.
Like for example, there are definitely complicated test cases here that we could potentially have. So like, let's say something like this, right? This may not
Mm-hmm.
exactly tell us where to go. So yeah, our implementation would definitely need to change. We'll have to have some like other cases to look at.
Yeah, so you potentially would have to end up searching like both halves, right?
Right, exactly. Or you can do a binary search, but you'll have to like potentially be cautious at certain points and kind of not greedily like reduce your search space by half every time, like you would do in a traditional binary search. There may be cases where you'd have to do like a more cautious search one by one.
Oh, okay. So you mean do like a linear search instead of just doing the binary search on like both the left and right side?
Yeah, there might be some cases like that. Yeah.
Okay, I see. Yeah. Okay, so we talked a little bit too about like this sort invariant that you assume is true of the input. I'm curious if your function had to also check that the input is indeed sorted, would you still be able to get a solution this efficient?
If we had to check for sortedness,
Mm-hmm.
so one way we are checking for sortedness is if at the very beginning, we have like a sorted case like this, we can automatically tell that it's sorted by looking at the first and last elements. Because in all of our cases, if it's not, because of the sort invariant, we can kind of instantly leave. So in this case, for example, the start is bigger than the end. In this case, the start is bigger than the end. But in this case, the start is not bigger than the end. So we can just do a constant time check at the beginning, like we do right here, to make sure that if it is sorted, we just return and immediately.
Right. So I meant in the case of like, what if your input is invalid? Because we assume that it is sorted, even if it's circular
Right.
sorted. If it is invalid, would you still be able to have a solution this efficient?
Well, let's think. We would potentially need to do, like, if we can't assume that it is circularly sorted, I don't think that we'd be able to do this in linear time. We'd either have to do some like validation, which may be linear, and that would bring us out of log n time potentially. We may be able to find where in log n time if there is an incorrect answer, but I think for verification we may need a log n an O of n solution.
Yeah, exactly. So a lot of this solution does depend on that sort invariant assumption. Okay, awesome. Thanks so much for showing us how you would answer this question today, Simon. I think this would be a great place for us to pause. I'd love to hear from you. If you were analyzing this interview as an interviewer, what do you think went well and what do you think you would change?
Yeah, so I think one thing that was good at the very top is that there's a brute force solution that we could do here, which is what we ended up implementing. And I think recognizing and sharing with you that it's likely not the most optimized solution, but that it would work was useful. You asked me to implement it anyway in this case, and it kind of set us up in a positive way by having me have these like unit tests that I could verify in this case, in the simpler implementation, but also in a future implementation where it is optimized. The answers will be the same no matter which implementation I use, but it's helpful to have like this unit test suite. It helps catch regressions like we did in this case. So I think in that sense, it was useful. One thing that at various points I stumbled on perhaps a little bit is that I didn't use an example immediately. And then later on, I recognized that before I implement or before I have like a algorithm correctness issue, I should probably use examples. And I think examples are really a really important way of figuring out how your potential algorithm would work. It can kind of help elucidate nuances, that sort of thing, guide you when you're unsure.
Yeah, exactly. And I think it also helps you communicate to the interviewer exactly what you're thinking, because it's kind of hard to like speak pseudocode out loud, you know. So showing
Right.
the interview, showing the examples definitely helps. And then you can
Yeah.
also easily catch your bugs if there is one. I also really like that you use the structure of the input to basically help you decide how to make the solution more efficient. So that being the fact that the input is already sorted, and as you mentioned, that is often a flag that binary search might be helpful. Yeah, so I thought that that was actually really helpful. And I also really appreciated, like, as you kind of mentioned, that this suite of unit tests was already set up. And it's not, I think I see a lot of candidates just kind of like write tests in real time and like run them one by one interactively. But this was just like a single function that you could run to check a ton of test cases. And I thought that was super helpful and demonstrated that you can write like more professional code.
Yeah. Appreciate that.
All right. Thanks so much again for being here. And thanks everybody for watching. If you have an upcoming interview, good luck. Bye, everyone.